Good evening and welcome, everybody. This is Obi-Wan Pez for N Simplex Pachinko. Do apologize for my chest cold. uh, Goodness. So, made it back from AMATYC after a um, kind of stressful journey. So I set out from home in the greater Balto Wash area and decided to go for the slightly cheaper route of flying out of Baltimore, Washington, and hung out for, like an hour before my flight was actually going to be doing anything. Why is this not working? Last time, kind of went about this and not really like, why did, okay. Apparently it just selected the wrong one, I don't know. Let's try that one. Anyway, hung out for a good hour before I needed to get through security and all that. Got through security just fine, went all the way down to my terminal where I was supposed to be, and sat down, got dinner. Flight wasn't supposed to leave until 6:30, so had a good, nice, long time to just relax and everything like that. And then somewhere around like, I think I started eating somewhere around 5, and then I got a text that my flight had been delayed. I'm like, okay, well, that's fun. And then we got more texts and more texts and more texts. Basically, every 20 minutes, they kept giving us another 20-minute delay. Lovely. And finally, at 9 p.m., there was no plane. There was like no plane in the boarding area, and they kept telling us that there was a mechanical delay, which was, mechanical issue, which was going to then finally at 9 o'clock p.m. cancel our flight. Meanwhile, we had all been sitting there, hopeful, for basically 3 hours. You can imagine how happy we were. So they tell us to go grab our bags, which had been unceremoniously dumped in the luggage bin outside of the security area. And oh, by the way, there aren't any more flights here anymore, so have fun. I was automatically reassigned to an 11 o'clock flight out of Dulles the next morning, which is in Virginia. It's quite a hike, especially since, I had been dropped off at Baltimore, Washington. And yeah, it's quite a tale. So 4 other people, no, wait, we were 4. 3 other people and I were tossed into a Uber, or maybe Lyft, I don't know. The guy did a great job with what he was given. 4 rather upset, tired, and angry people who just wanted their goddamn flight out to Toronto. So, the Air Canada people were very kind in letting me know that I could, in fact, because I asked, I could in fact switch to the 6:20 in the morning flight, which would then arrive in Toronto by about 7:30 or 8. And yes, please, I would like that one. I was informed that I was the last person who was swiped that particular route and managed to get a seat assignment. I believe everybody after me then had standby printed on theirs. Or they were assigned to one of the other 2 flights that were that day. Whatever happened. Don't care. Then our Uber driver is heading down that way, and the lady in front says, I'd like you to divert over to, Marriott or whatever. That's next to Dulles. And guys, of course, I'll do that. So pretty much all of us just sleep the rest of the time that we drive. We make it to this Marriott, and I get in line, and the 2 people ahead of me are like, yeah, book us, rooms because we got to stay the night. And I wasn't listening at all. And I got up and I was like, yeah, same thing for me. And the guy's like, yeah, nightly rate's $300. I'm like, never mind. Reason being, it's only like a mile from the airport. So I called another Uber, which then got me to a Best Western, which was very nice, very lovely, and only cost me $150. But nonetheless, it was a stressful time. I then climbed into bed at about 11:50 p.m. and set my alarm for 4 in the morning. You can imagine how that went. So, after waking up at 4 in the morning, I had to then get everything packed and downstairs and into a shuttle at 4:25 for a 4:30 shuttle over to Dulles, and the other guy who had not gone into the rather expensive hotel had shown up at this one. I was like, hey, I remember you. So we both made it on the flight. Both made it to Toronto. Said see you later. He was not at the conference. He was doing something else. Nor were the other 2 people, as I didn't see them. It's not necessarily, there's a lot of conferences going around in any city. It doesn't matter. Anyway, had a lovely time at the conference. We'll talk more as we go. Blainland, I don't know exactly what you mean. So what exactly do you want out of conversion of kinetic energy? So there's the example that the guys over at Numberphile did, which I found rather interesting. The only real things that I know about here are you look at the different kinds of energy that exist, and you say that, well, the sum of all the energies has to be equal to the original energy that was in the system, regardless of what is there. Since, again, no energy can be created or destroyed, it can only be converted from one type to another. So, if we're talking about like a swinging pendulum, then we would be looking at the conversion of gravitational potential energy into kinetic energy and then back into gravitational potential energy. The problem there is that we have potential air resistance, thermal energy of the parts of the system that are all heating up. If there's any sort of chemistry going on, that could also affect it. So we need to know more about the system that we're talking about in order to really understand what it is that we've got. And believe it or not, this is not Concrud. This is just a like bronchial nastiness that I had slightly before I left. It was a lot worse. Now I'm just coughing up all sorts of fun stuff. So, the con was wonderful. So AMATYC, the American Mathematical Association of two-year colleges, puts on an annual conference. Next year, we are going to be in Omaha, Nebraska. Woo! Everybody's like, yeah, college baseball Hall of Fame. I'm like, yep, okay. As much as I would like to go to another AMATYC, I think I need to take a year off, let some other people potentially go, since I'm not really doing anything at it. Like, I'm not part of the leadership team, I'm not anything like that. It's not likely that my school would fund me multiple years in a row. Maybe needed some honey on this. So when I finally made it into Toronto proper, actually there's more to the story. It's kind of amusing. Got off the plane and said, you know, where do I go for train into the city? Because there's a train. There's lots of trains. I don't have a bus pass or anything like that. I'm pretty sure you need a bus pass if you're going to do the bus. So, I told the guy, like, okay, buses are on the ground floor. Sounds great. Do you need, like, a pass or something like that? He's like, yeah, you can get a pass. But otherwise, you can go and get either one-ways or return trip tickets, two-way tickets for the train. And I was like, yeah, the train's probably a better option for me. So he said, just follow the signs. They all say train. And I was like, yeah, okay, they all say train. So up the stairs, over the skywalk to the other building, and walk in there to see, there's a train that's already there. And I'm like, great. And it's like, leaving now, be back in 15 minutes. I'm like, all right, cool. So I rush over to the ticket machine and start like looking over my options, and then it's like, what station do you want to get off on? I'm like, I don't know. And then I pull out my phone and I go, all right, I don't have international roaming, so I have no internet. Yay! So eventually I find out, yes, you can in fact pull up Wi-Fi at that particular place, and Wi-Fi pretty much always works everywhere. So provided you are not in the middle of the road or something like that, you can pretty much hook in just about anywhere. Both the airport and the train station, the up station, have Wi-Fi available, so I can at least look at the map and see where I'm trying to go. And so I plug in like the different station names down the list to try to see where I'm going. Then it says like, yes, you want to go to Union. You are at Pearson International Airport, YYZ, Toronto. You want to go to Union Station, which is downtown. I was like, okay, that's great. So I purchased a Union ticket, and then I jump on the train that is right next to me. And I go about a stop, and I said, hey, so where's this going? And there's a pilot who had jumped on just after me, and he's like, this is parking. I was like, that's not where I wanted to go. So I was going out to a parking lot. So 15 minutes later, the tram comes back, carrying me and a couple other people from, the other side of the parking lot campus there. They, drop me off. I have a ticket, and I'm like, yeah, right there. Cool. So I grab my stuff and I run up there, and they just close the doors. Next train's in 20 minutes. There were 2 people ahead of me, so I didn't feel too bad, right? Like, I couldn't have made it onto the train. They would have stopped me. So, okay, whatever. But still, had I not made that little blunder of going out to the parking lot and back, I would have made that train. Had I not made the blunder of just purchase a ticket, you probably know it's going to go to Union, go. It has a little picture of like buildings. I should have figured that was it. I probably could have gotten on the first train instead of the 3rd train. But again, whatever. It's fine. It's Canada. Everybody's pretty happy. So we walk up there. I'm standing for maybe 2 minutes before the next train comes, and then we all get on, and it's another like 15 minutes before it actually leaves. Still ahead of time. Ahead of schedule. So we make it all the way into downtown, and I'm like, all right, this does it. I need coffee, and I need directions, and I need to figure out what exactly I'm doing. I also need breakfast, because coming from Dulles, I had 0 food, because it didn't open until 6. And they were like, yeah, there's a Starbucks that's like 2 terminals over, but it's going to take you 10 minutes to get there, 10 minutes to come back, and an hour in line. And I'm like, yeah, nah, I'm good. So I had a ginger ale on the flight. That was about it. Go to a nice little place called Balzac Roasteries. Yeah, little place. It's a franchise. Never heard of it. End up getting, small, I don't know, scone or something like that with a coffee. And we end up, I end up figuring out where I need to be. I need to basically just go outside and then figure out which way to go up like 10 blocks. And I'm good. It's pretty much a straight shot to my hotel. And like a couple of blocks over and a straight shot to the conference. So, cool. I'm within like, I think it was 800 meters. So, within like half a mile-ish of walking. Not too bad. I don't need a ride or anything like that. So, grab my stuff, walk outside, and the first blast of cold air hits me in the face. I'm like, oh, okay, it's going to be like that. It was, I believe, 28 degrees or something like that, and I hadn't actually put on my coat yet, because I was just like, it's going to be cold, but... So, yep, there was a nice little area. It was like going to be probably 200 meters to go either direction on the block to go all the way back up to the top of, or to the next block, And then I found that there was a nice little stairwell just across from where I was. So go up the stairwell, wonderfully icy everywhere. Come up, go over the top. I can't check into my hotel until 3. So it's 8 in the morning. I'm like, well, you know, I could go to the hotel and convince them to hang on to my bag. Eh. Yeah. It could get like that. So, Blainland, if you heard me from before, the conversion of kinetic energy, I need more information in terms of what you're trying to do. I mean, you say that, but you also got an A in your previous calculus class. So, like, yeah, and that's true. Word problems always need um, need decoding. So toss out the irrelevant information, bring up anything that is relevant, and you know, what is relevant and irrelevant is not an easy concept, especially if, yeah, especially if that's the case. All right, cool. That also depends on which part you mean. But if you mean just parametric equations altogether in general, we could do something like that. So, yeah, but like eventually you're going to need it. Or if you want to talk about something else, we'll talk about something else. um, well, it would be multivariate calculus, but if you're done there, physics, and anywhere that you find yourself kind of stuck by the fact that you can't create a function. So let's say that this is my walking path for, I don't know, something crazy. Probably not, because discrete is usually about doing proofs. So this is a continuous function, which is kind of the antithesis of discrete. I mean, you say that now, but like there is the possibility you'll come across something that was like, oh, I'm sure glad I learned how to do this. Because otherwise, like I would have had to figure this out completely by myself from zero knowledge. At least in some way, you might have a passing knowledge of whatever that particular thing is. All right, so what we see here is just a curve that is, this one is continuous. Starts at this location x0, y0 and ends out here at x sub n, y sub n. You will also notice that there is a t variable here. This can correspond to time. So for instance, this may not be a function in x or y, but x and y at least can be, don't have to be, but can be functions in t. So what we can do is create some sort of function f of x is equal to, and up here we can do a, not f of x, f of t is going to be equal to a parametric set of equations, which is x of t is equal to something, and y of t is equal to something. Each of these individuals are going to be functions of t. So for each of these x of t and y of t, there is some sort of function which will define this particular path. All right, and this path can be defined by a set of parametric equations. I don't know what that parametric equation would be. It could be piecewise, it could be all sorts of other ugly nonsense, but nonetheless, for any one time, we have one and only one location, x, comma, y. That will be the outputs for this particular function. In fact, this f of t might be better stated as f of t maps to xy, like that. So every particular t value is going to map onto an xy coordinate pair. And again, these may be completely, very extremely complex functions and all that, but nonetheless, this will map every single point, or every single t value, t0 all the way through tn, so that we have a corresponding x and y value, which are unique. No, which are not unique. The t value is unique, which makes it a function. Right, so it is a function in t. So when we've got all sorts of other stuff, like x of t is equal to t squared minus 1, and y of t is equal to 5t minus 3. One of the things we can do is create a table of values for this. So I've seen this done both ways. Right, so our t value, for instance, for this might be t goes from, say, 0 to 5. 5. Yeah, 5 will work. That's not what I wanted. Bracket. So if we go make a table of values like this, we can then plug in individual t values back into this stuff. So x of 0 is going to be -1. Y of 0 is going to be -3. X of 1 is going to be 1 squared is 1 minus 1 is 0. And y at 1 is going to be 5 minus 3 is 2. Okay, 2 squared is 4 minus 1 is 3. And 5 times 2 is going to be 10 minus 3 is 7. Okay, if you could see the pattern, for instance, this is a linear function, so it's going to be super easy. We can now add 5 to each of our y values as we go up. This is just going to be 12, 17, 22, and 27 if we kept going from there. Meanwhile, on the top side here, we've got 3 is getting plugged in. It's going to get squared is 9 minus 1 is 8. 4 squared is 16 minus 1 is 15. And 5, 25 minus 1 is 24. Okay, so if we go like this, so we go 5s. Okay, so I misjudged that. We need to go to -1, -3. So -1's about here, -3 is about here. We have here t equals 1 at 0, 2. So x is 0, y is 2, about here. So these are going to be all x, y coordinates. I should really involve the t as well. So this is t, x, y. T in this case is 1. X is 0, y is 2. Okay. At t equals 2, x is 3, y is 7. Somewhere around here. 3, 8, 12. Four, 15, 17. So 15, 17. And 5, 24, 22. 24, 22. This is going to go like this. All right, who in the class can tell me what kind of function that is? So in terms of x and y, this actually does have a function representation as a y as a function of x. And if we want to figure out what that particular relationship is, we can take this stuff and translate it back into rectangular form. Say this is our x, this is our y. Again, txy is also telling us, this is something else I should have, the direction of flow of this particular thing. So it's showing us how it's moving. Here, we've got x is equal to t squared minus 1. We would like this t here to be replaced by whatever this is up top. So here, we should solve for t. This means that x plus 1 is equal to t squared, and that the absolute value of t is going to be equal to the square root of x plus 1. We only want the positive version, as we can see here. So t is equal to the square root of x plus 1 for this particular example. Alright, so t equals square root of x plus 1. So then y is equal to 5 times t square root of x plus 1 minus 3. And then if we look at this, we're going to notice that this is indeed what we would get for a standard square root function that's been transformed by a vertical stretch factor of 5 and a downward shift of 3 and a leftward shift of 1. Alright, so how about this? Well, we can do the standard TXY table of values. Which values are going to work nicely? Well, these are trigonometric functions, so t should be multiples of pi, factors of pi. No, multiples of pi. But it doesn't have to be integer multiples, so we can go with, like, you know, pi over 6, pi over 3, all that good stuff. Check. Yep, okay. Weird. If we go with 0, we'll see that the cosine of 0 is going to be 1. Sine of 0 is going to be 0. All right, so we get our distance of 1 here. And if we go to stuff like pi over 4, we end up with root 2 over 2 for both of these. So you can see pretty clearly, well, this is now going to be just the regular unit circle, which is then pathed this way. Ish. So from 0, 1, 0 to 2 pi, 1, 0. Just once around the circle. Alright, so t is going to go from 0 to 2 pi. Alright, so this is what we get. Interestingly enough, right, you could have done any set of functions, so why not x of t is equal to the sine of t, and y of t is equal to negative cosine t, right? What does this produce? Well, if we were to do this just as written, again, TXY table. I mean, I rarely ever use a table of values more than with parametric equations. Alright, with a t value of 0, our x value here is going to be based on the sine of 0, which is going to be 0. Our cosine value, y, is going to be based on a negative cosine of t. So this is going to be cosine of 0 is 1, and then it's just made negative. So 0, 0, negative 1. Well, where do we start now? right? 0, -1. So then if we do pi over 4, this is going to take this as root 2 over 2. And y is also going to be root 2 over 2, but then it's made negative. So now this is going to have a positive x value, root 2 over 2, and a negative y value. So pi over 4, root 2 over 2, negative root 2 over 2. Okay, this is going to end up going like this-ish. Oh, man. That's pretty close. So here, this is going to be taking our t value from 0 to 2 pi, but it's going to make the individual function that we're looking at completely different. In this case, it's a circle that starts at the bottom and does actually continue around counterclockwise. So parametrics are rather fun. You can create basically anything you want out of it, as long as your original function can be mapped by some parameter. In this case, the parameter that we're choosing to use to try to better describe the features that are going on in order to better describe the function itself that cannot be defined as y as a function of x is going to be, again, here. X is a function of t. Y is also a function of t. Bring them together and couple those equations. So that's why they have a square bracket around both of them, like that. That's saying that this is a coupled set of equations. And yes, this could, in theory, produce a three-dimensional graph. All right, if you treat time as yet another spatial dimension, then as we go around the circle, this could also trace outward like that and make a nice little helix shape to show how time is moving. Okay. So whilst at the conference, I was staying at the Rex Hotel and Jazz Bar. No, I am not kidding. So if you're ever in Toronto, I do recommend at least stopping by the Rex on one of their for one of their shows. They have 5:30 and 8:30 p.m. shows nightly. 7 days a week, and unless they're on like a public holiday, in which case I don't even know if they take the time off, but they have enough staff. I think they can spread it around. But at any rate, yeah, it was really nice. The room itself was basically like a college dorm. I mean, it was a tiny single that was stuffed up on the second floor of this restaurant / hotel. I chose to have a private bathroom, which maybe wouldn't have mattered all that much, but it was a good thing I had it because I was, like I said, kind of hacking um, the entire weekend, and wouldn't have been terribly much fun if I had nowhere to put that. So ended up getting up and getting rid of it in the sink so much. That part of it was not so much fun, but and then went and saw the keynote address on Thursday was by a guy named Peter Liljedahl, who was or is still a Canadian professor of mathematics. He is at a 2-year college. He was, once upon a time, back in 1992 on the not US, he was on the Swedish Olympic Canadian style canoeing team. Canadian style canoeing is you have this kind of like triangular boat that's really super long, and then when you get on it, you kind of kneel, and then you're going to canoe this way by digging into the water and coming back up like this and just going again and again and again. His event was the 1,000 meter. So yeah, a whole kilometer of just nothing but pulling. His keynote expressed that his life had taken some interesting turns and all that, and he ended up in math education. And while studying math education as, I believe, a postdoc, he did some research into trying to make the classroom a better, more inclusive space for all different types of learners and stuff like that. So he said, we're going to, anybody who wants to jump in on this, and we're going to study these like 6 variables that we think will affect teaching. And so he and the group that were selected, like 100 some odd teachers that put in all of their classes, or decided to change their teaching style to fit whatever it was that Peter wanted them to do. Some of them opting to do or not do certain teaching practices. So they isolated all these variables to try to make sure it worked, and pretty much immediately it became obvious that this was insufficient. So they needed to do more variables, and got many more teachers in on the whole study in order to increase the sample size. And they identified 14 variables, which ended up being useful in trying to figure out what was going to happen with all of these students. How are they going to learn based on like this educational profile that they created? Well, as it turned out, pretty much every single student did better under every single change individually. And the ones that far outstripped everyone else were those that had like every single one of these particular changes done. Many of them end up being like sort of semi-possible. Others, for like without serious like reformation of your particular classroom. So me see if I can pull up the... Oh, you know what? I can pull up the chapter list from the place I got it from. Um, where did I get it from? Yeah, it's just chapter 1. Okay, good enough. Okay, here we go. So, oop, give me 1 minute. Okay. Welcome back. So, there are identified several individual pieces which were super important, others which were, moderately important, other stuff like that. So, um, I mean, this is, if you read the document for it, it's pretty comprehensive in terms of like the ridiculousness of just like how many variables were tested and how, how rigorous was all of this testing and stuff like that. So they determined what the average times were that students were spending on a particular task and tried to figure out, this is an average. They gave one group a vertical whiteboard, one group a horizontal whiteboard, one group a vertical paper, one group a horizontal paper, like the big papers, and one just use your notebooks. So as it turned out, the time it took them to like start on the task, the time it took them to get to like doing notation, and the time that it took them to like get engaged in this particular oh no, and the um, seeming eagerness of this particular group to like get on task, do the task, and get to it ended up correlating very strongly. So the time to get to the task was pretty much the same for all of the groups. It was somewhere around 13 seconds. Sure, whatever. The time to like actually start writing notation on it for the vertical whiteboard, the horizontal whiteboard, and the notebook was less than 24 seconds to like start writing the equations that you needed to. The vertical and horizontal paper took them more than 2 minutes to like get out there and start writing what they needed to do. Tiff loves weed. How you doing? My name is Obi-Wan Pez. This is N-Simplex Pachinko. I am discussing the findings of a rather interesting study. Um, which was to get like math students much more involved into into doing a task and stuff like that. So very nice. Well, welcome on into the channel. If you have any questions about mathy type stuff, or whether that be content or pedagogy or anything like that, let me know. And otherwise, just feel free to hang out. Oh, thank you. Right now it is really crapped up because I've got like this, I don't know, head or chest cold. But it'll be coming back pretty soon. It is pretty low normally, so. So yeah, time to get to the task was pretty much straightforward across the board. Everybody's there. Okay. The time to write down notation was almost, what is that? That's 6 times higher for both the vertical and horizontal paper. And so the way that they tried to figure out like why this was, or the reason for why this was, they think, is because students were really reluctant to write on the paper because it's like, it's permanent. You can't just flip to a different page like in your notebook, or on a whiteboard you could just erase everything. So on the like giant strips of paper or giant sheets of paper that your group gets, they didn't want to waste the space. So they had to like talk about it first before they did that. So it took them a really long time to start writing. And the eagerness by which each group was working seemed to be very low for both the notebook and any of the paper stuff. The group seemed to be at least twice as eager for whatever they were measuring for both the horizontal and vertical whiteboards. The amount of discussion that was there was almost double on both the whiteboards compared to the papers and the notebooks. So, like, what is going on? Thank you very much. No, it's not particularly weird. I think it's just the internet. If you got to know me, I would be incredibly, probably incredibly boring and weird. But then again, who probably isn't? So, the amount of participation that these groups engaged in was ranked at a 2.1 for horizontal whiteboard and a 2.8 for vertical. Whereas in the vertical horizontal paper, it was 1.6 and 1.8, and notebook was 0.9. So it's like a lot lower. The persistence in which the groups like kept working at stuff, even if they had setbacks, they kept coming back and being like, nah, this is not working. Okay, let's try something else. Let's try something new. Let's do something else. anything at all. They ended up with rankings of 2.6 on the whiteboards versus like about 2 on the papers, whether that be papers or the notebooks. Non-linearity of their problems. So like having just thoughts and stuff like that, kind of zipping all over the place, not always setting things up in this very straightforward whatever. um, on the whiteboard, it was just free flowing and all these ideas were thrown around. And then when it came to presenting, they would then be able to take those ideas and put them in a specific place to say, this is how we're going to lay it out. But everywhere else, they were just like, we could toss around any ideas we want. But on the paper, it was like, well, we have to start immediately into putting things into this regimented form because we only have this amount of space. And then on the mobility, so being able to move around, being able to talk with individuals in the group, being able to shift and be like, no, you write it, and then have somebody else write for a little while, and like, oh, I've got a great idea. Everybody moves over and gives that person space. Giving people space was super high on the vertical versions and fairly low on everything else. And so using this data, they were like, all right, let's start by immediately implementing vertical, non-permanent surfaces. So we're hearing this term, non-permanent surfaces. So I first heard this term probably about 2 weeks ago. And then I went to a conference and Peter starts talking all about vertical non-permanent surfaces. I was like, oh, yeah, I read about that. It was probably his study. Or something that was based on his study. So vertical non-permanent surfaces are allowing these students to do more, to be able to get up there and throw their ideas around more, to be able to shift around and be like, you write this, you write that, a great idea, you do it. So this is becoming like the big thing for the next, I don't even know, like tiny amount of time, doesn't matter. For the next few weeks, like this is always just going to be talked about. All right, and then next they said, based on this VMPS study, they're like, let's try looking at what's going to happen if we put students into differently sized groups. So if we put groups into like individual, like working on a problem individually, versus if they're in groups of 2, groups of 3, groups of 4, groups of 5, groups of 6, what's going to happen? And so they start looking at group size. And the team finds that the optimum group size is 3. All right, if you only have 2 people, sometimes the 2 people don't always play off of each other exactly the way that they want to. They don't have as many ideas as 3 would. Now, granted, that isn't as many as 4. So why wouldn't like 4 or 5 be better? And the point here was that after you start increasing the group size beyond 3, now you have maybe one person who's more willing to just kind of step back and maybe slack off a little bit, not do the engaging work of getting into this group and talking more, trying to talk about mathematics. So the optimum group size ends up being 3. And then they start talking about group selection. So how do you select groups? And specifically, if we always want to try to get groups of 3 as much as possible, how should we get these groups selected? So first of all, The ideas are that you could do random, you could do non-random, or you could do choice. Immediately they found that choice was a terrible idea. Students don't know what's good for them. So they start picking their friends instead of people that they're actually going to work with, or they're going to pick people that they're going to work from, perhaps, instead of working with. And then also with non-random, so like teacher's choice, it ends up being that there's this like social hierarchy that starts coming about. So again, you've got your like high achievers versus your leeches, as somebody called them. That's spelled wrong, isn't it? Yeah. Yep. So there's this social hierarchy that forms where you've got like, again, got your workers, and then you've got your leeches. Then you've got people in the middle, or still more toward the bottom, I guess, who are kind of apathetic. And then all of the work gets dumped up onto the workers. So that's not going to work after enough time. So they said, okay, don't do non-random. Make it random. And when they started making it kind of like random, like the teacher figures out a random grouping ahead of time and then just comes in and says, here are your groups, students found that there was also sort of this hierarchy that was forming a little bit, but it was also like they started feeling kind of resentful that, like, I don't have any control over this. It doesn't make any sense. Like, how did you pick these groups? And when the teacher said, oh, it was random, like I, pulled out names from a hat and stuff like that, they were like, I don't know. So they didn't really trust the teacher in that sense. There was a loss of trust. And so because of that, Peter said, make sure that this is visibly random. So like in the moment, draw cards. Allow the students to be able to do the random thing. Make it part of the activity. Yo! 3 left seconds. How's it going? Apologies for missing last week. I was prepping for AMATYC and, oh man. Did you take it? How'd you do? If you feel like talking about it. Ah. Do you get to work on that and try to like improve that area? Or are they just like, nope, never? Yeah, I don't blame you. What'd you want to go into? Which category did you miss? Was it was it math? Yeah, yeah. I had my full breakdown when I took it out of high school. So it was like, you know, um, hmm. Oh, right, because it's electronic these days. Of course it is. Yeah, mine was entirely on paper. And so we had the three groups, which was like or no, the two major groups. So it was like math and um, like linguistics, language, English, like comprehension, that sort of stuff. And then we had the list of all of the different career path um, sort of things that you could go for. It wasn't really career paths. It was like information coding and mechanics, right? So mechanics, I got like a 39th percentile or something ridiculous like that because I didn't work on cars. Like they're talking about torques and stuff like that, and I'm just like, no, I want to be a physics student, but like that's different. And then of course I didn't care because mostly I was trying to get into the nuclear sub program, which I did, but never actually joined. But so group selection, make it obviously, visibly random. Get the students involved if they can, and often change. Like I said, about every hour or so. Um, so this is stuff that is real easily done. Oh yeah, go for it. I'm just talking math pedagogy that I learned about this week while I was at the AMATYC conference. So vertical non-permanent surfaces, group size optimal 3, group selection, do it visibly and do it random and do it often. Yeah, D front. The classroom. So stop pretending that the front of the classroom belongs to the teacher. All right, go walk around and do stuff like that instead. Okay, so algebra. Mm-hmm. So like 3 times the quantity x minus 4 is equal to 16. So if you got stuff like this, you're going to say here, what we've got is the product of two numbers. Those two numbers are 3 and this thing. Don't worry too much about what this thing is. Just ignore it because there's more work that needs to be done there. But if you don't like the way something looks, the point of algebra is to say, all right, this is B. This is just a thing now. So 3 times B is going to be equal to 16. So how do we solve for B and get it by itself? Well, you do the opposite of whatever we have here. This is multiplication. So the opposite, the thing that undoes multiplication, is division. You have to divide both sides by the same thing. And the thing we want to get rid of is the 3. So B is going to be equal to 16/3. But B is equal to this thing that we had up here, x minus 4. Now we see that here we have an expression that needs to have x by itself, and it's attached to a minus 4. So do the opposite. We're going to add 4 to both sides. So x is equal to 16/3 plus 4. Then 4 by itself. Four by itself is going to be here. We need a 3 in the denominator in order to add to the other one. But if we're going to do that in the denominator, then we need something up top to balance it out. So it's going to be 3/3. So we are multiplying by 3 divided by 3 is 1. When you multiply by 1, nothing changes. So in this particular case, we want it to not change because we want to introduce a new denominator. All right, 4 times 3/3. Equals 16/3 plus here, 4 is 4/1. And when you multiply, you go straight across. I mean, presumably you could probably get it by now in terms of what the like multiple choice are going to be at this point, but you know, it's worthwhile. So here you multiply straight across. 4 times 3 is going to be 12, divided by 1 times 3 is going to be 3. Then here we've got a 16 and a 12. Those are our numerators. They tell us how many of these things there are. And then the denominator is telling us how big these things are. So here we have 16/3, and then we're adding 12/3. So as long as our units match, then we can add and subtract stuff. So here this is going to be 28/3. So if you are evaluating, then yes, you are plugging something in for x, and then you are evaluating what it is. So plug 6 in, right? 6 minus 4 would come first because it's in the parentheses. So 6 minus 4 would be 2. And then we multiply by 3 because it's the next thing outside the parentheses. There's no exponents here. So times 3, 2 times 3 is 6. 6, the whole left side, is not equal to 16, so it can't be 6. X cannot be 6. So if you're trying to solve something, you have to go in reverse order. Think of this like, you know, PEMDAS there has created a giant dog pile of people who are scrambling for the ball in football. The X is the ball. You gonna start in the middle? Try to figure out who's got it? No. What are you gonna do? You're gonna start on the very outside of the pile. You're gonna grab the collar of the guy on top and go, get out of here. Come on, out, out, out. And try to wade through the crowd to get down to the bottom to see who's got the ball. So here, this is what we're doing. we're saying that we've got this 3, which is the outermost bit. So you can also do that if you want, because that is distribution. But the point is that you are, one way or the other, dealing with that 3 first. You can decide if you want to distribute it in or if you want to get it out. In this case, we got it out. So we said, all right, divide by 3 on both sides. Take the furthest guy off the pile. Toss it. Nah. I mean, yes, you can do it the other way to avoid fractions. Because it does actually make it the last thing. So one way or the other. So the distributive law says that we take 3 times x, and then we're going to add it to 3 times -4. That gets us our 16. Now you could also say that this is just going to be a minus here instead. Doesn't matter. So 3 times x minus 3 times 4 equals 16. It's all the same stuff. Sure, same thing. This is one of the other things. If you recognize the pattern, right, it's going to be all the same stuff. This is going to be the same behavior. 3 times something, 4 minus 2x, is equal to 6. So here, again, you could distribute in, or we could divide out. In this particular case, this is divisible by 3, so that makes it nicer. So 4 minus 2x is equal to 6 divided by 3 is 2. And then here, my preference is to make your variable positive and then get it by itself. Here, 4 minus 2 is going to be 2, plus 0 is equal to 0 plus 2x. Divide both sides by 2. X is going to be equal to 1. Again, if you want to distribute first, you could just as easily have done that. So here we get 3 times 4 minus 3 times 2x is equal to 6. So here, 12 minus 6x is equal to 6. Again, my preference subtract the 6, add the 6x to both sides. We get 6x over on the right, and then here 6 on the left, which again, divide by 6 in both cases. X equals 1. Oh, sure. 4x minus 7, parentheses, 2 minus x is equal to 3x plus 2. Alright, so again, you can do multiple things at once here. Anything that's separated by addition, subtraction, you can move around. So here we want to combine like terms. So here subtract 3x from both sides. This 2 can stay over here. This we're going to distribute in. So this is going to be 4x minus 3x is going to just be x. So because those things are separated by addition, you can do those things at the same time. It doesn't actually have to be one then the other. Let me rephrase that. Because these are separated by addition and they don't interact with each other, right? So this negative 7 times the parentheses 2 minus x doesn't really affect when we subtract 3x from both sides, right? It's not involved because that involves just these two terms, 4x minus 3x. So anytime that you're trying to do something, you could say, is there anything else that I'm not touching? And then can I do something with that that's going to like move us forward? So in this case, doing the distribution is independent, does not affect these values, 4x and the 3x. So we can combine them. Sorry, we can combine this into one action. So here, a negative 7 is going to multiply into a 2, and we get a minus 14. Negative 7 times negative x is going to be a plus 7x. How about that one? Yep. So because it's a negative 7 multiplied by a negative x, it's telling you to switch the signs every time a negative interacts with something. Every time a negative multiplies by something, it's telling you to switch the signs. So our base sign is a negative, and then we're multiplying in a negative 7. So a negative switched is going to make a positive, and then 7 times x. Yeah. This is just algebraic manipulation. So like shifting stuff around is okay by the various rules that we have come to understand. So this right here, for instance, yep, that one's super easy though. All right, what's the volume of a rectangular prism or a box or anything like that? So this one here, we've got an x there and a plus 7x there. Some of my students get really tempted by this and decide that they're going to subtract 7x from both sides. Now, I can appreciate what they're doing, but this is not going to work because the equality sign's over here. And in order to subtract 7x twice from the same side, we're going to need a negative 14x subtracted onto the other side. That doesn't really work too well. Right. Because they're on the same side, all we're really doing, right, think of this in terms of like a friggin' pan balance, like this. Right, so all we've really got is 1x over here, and 7x's over there. And then negative 14 over here. And then over on the right, we've got a 2. And these are in perfect balance with one another. You can't see that. These are in perfect balance with each other. If you try to take stuff off, then you better do it on both sides. But if you want to combine the x and the 7x, you just say, well, they're on the same side, so how many do we have on that side? It's 8 of them. So 8x's. Minus 14 is equal to 2. And again, just like we did before, this is going to add 14 to both sides. This is 8x is equal to 16. Divide by 8, x is equal to 2. Page not found. Good evening. My name is Obi-Wan Pez. This is N-Simplex Pachinko. Hopefully your new home for mathematical stuff. If anyone is interested in submitting problems or discussing stuff, feel free to drop it in the chat, and I will get to it as soon as I can. I am feeling like I am going to drop out here pretty soon, though, because I'm probably about to fall over. So, it's fun. Curio, thank you. Good evening and welcome. My name is Obi-Wan Pez. This is N-Simplex Pachinko. Is there anything I can help you with tonight? So, volume, really it all depends on the shape. Because, like, all sorts of stuff has all sorts of different volume equations. However, there are some basic categories that you can break it down into. So if you want the volume of a prism, you're going to need the area of the base, whatever it is, times the height. That is always going to be the case. And this also works if it's slanted. So if you have a cylinder, for example, that is slanted like this, even if it's curvy, it still works, as long as it is curvy in the same direction on both sides. All right, so this does not technically work, but we could pretend. So if you have this curvy sort of thing here, what we've got is a height. It's given by this distance. How far is it from the bottom to the top? The bases have to be parallel to each other. And then here, all you really need is pi r squared to find the area of a circle, or whatever other shape it is. So it does not even matter at all what shape it is. You'll be able to find the volume of this particular prism, because a cylinder is a prism, even if it's a slanted prism, by following the exact same thing. So area of the base times the height. Monomial and binomial quadratic equations involving three-dimensional functionality of coils, prisms, cubes, and cylinders. Goodness. Not sure I know the... I'm not sure I know what the three-dimensional functionality of coils, prisms, cubes, and cylinders might be, but we'll investigate that. Hey, Pen Center. How are you? Yep, so the only thing that really matters for height... yeah, pretty much. I'm not going to tell you what the Canvas app has for a number. I might literally get fired. I'm not doing it next year. I'm not doing the same thing. This is just absolute nonsense. Like, the exams are bad enough. Okay. So, 3 left seconds. The difference between height and length is the direction that it's pointing and what we choose to call it. That's it. Because you could call this the length, sure. That's fine. But colloquially, you'd probably think of the length as the slant length. So the length that goes along like the side of the cylinder. That's not what you want for this case. Now, there are better places to choose. For instance, from like either the side or somewhere over here in the one circle compared to directly above or below where the other circle is. So instead of being out here in imaginary land. But you are just measuring this to the top of the cylinder anyway. So bottom of the cylinder to top of the cylinder, base to base. So anytime you want the volume of a prism, try to find the area of the base and then multiply by the height. Again, height or length is the distance from one face to the other, opposite each other. Direct line distance and all that, yada yada. All right, difference between height and length. Or we just did that literally. Wow, I'm okay. So Pen Center, this is I'm just curious if you can parse the second part. Monomial and binomial quadratic equations is simple enough, but Sorry to call you out, Paige. Okay, so 3 less seconds. If we go like this, we say that the area of a circle is going to be equal to pi times r squared. And V, volume of the prism, in this particular case, is going to be pi r squared times our height. So if we know, for instance, that this has a radius of 5 centimeters and a height of 20 centimeters, then here we'd say that we've got pi times r is going to be 5 centimeters squared multiplied by h is 20 centimeters. I know that here this is going to be square centimeters and this is going to be another centimeter. So altogether this ends up being 25,500 pi multiplied by, or no, not multiplied, 500 pi cubic centimeters. Okay, and volume of a pyramid is going to be very similar. So any pyramid that you create from a prism, so basically you just take one of its sides or one of its bases and you collapse it down to a single point. So we have like a 1, 2, 3, 4, 5, 6, right? So heck, yes, thank you, whiteboard. So collapse all your points down to one single point, like that. And this now becomes a hexagonal pyramid, hexagonal based pyramid, instead of a hexagonal prism. That's what I wanted. Oh. Okay, so we have a hexagonal prism here. So if you want the volume for a hexagonal prism, it's right there. If you want the volume for a hexagonal base pyramid, it's right there. Now granted, you do have to figure out what the area of a hexagon is, but it's not like huge problem. Woo! Out of like a hose. Yeah, so cubic feet is a measurement of volume. So he would not be losing volume unless, of course, he's vomiting while he's falling. But that's not actually volume. Never mind. Yeah, that'd be his weight is being lessened. Yeah, that's not a. So if a bird has entered free fall on an upward trajectory and then decided to just not open its wings, its path could look something like this. Actually, it'd be a little bit steeper when we start going out here, but so let's say a bird is here at no 300 feet up in the air, and it's on an upward trajectory. Initial velocity is going to be 50 feet per second. So based on an upward velocity of 50 feet per second and starting at a height of 300 feet, we would want to know, for instance, what is the height of this bird at every moment in its free fall. So the height equation for this honestly should be given. Is 1/2 AT squared plus V0T plus H0. Okay, so A is going to be the acceleration due to gravity, which caught me by surprise. Sorry about that. Acceleration due to gravity, which in Earth's gravitational field, the acceleration due to gravity is very approximately a negative 32 feet per second squared. So what that is it's the for every 1 second that passes, what is the change in velocity feet per second? So if you change your if you're in free fall for 2 seconds, then your speed will change in a downward direction or a negative direction by 64 feet per second. It's nice and easy and just kind of rolls off the tongue when you start getting it one right after the other, because again, it's just going to be like, after 5 seconds, it's going to drop 160 feet per second, or it's going to go downward at a faster rate by 160 feet per second. So in this particular case, same thing applies, but then we also have to take into account our V0, which is the initial velocity that was given. So that's going to be 50 feet per second, and its initial height, which was 300 feet. So here, a negative 32 is going to make this a negative 16 t squared plus 50 t. So our initial velocity is 50 times t plus h. It's going to be 300. So if we wanted to know what h of 5 is, what the height is after 5 seconds, then this is going to be a negative 16 times 5 squared plus 50 times 5 plus 300. This is going to end up with a negative 16 times 25. So if there's 4 of these in 100, that's going to end up making 400, and that's a negative value. Okay, plus 50 times 5 is going to be 250. Plus the 300 that was already there. Okay, so negative 400 plus 300 nets a negative 100, plus 250 is going to be 150. This being height, h, it's 150 feet. after 5 seconds. All right. I think that's going to be it for me, though. I'm not entirely focusing. Literally. So we're going to try and see if we can find somebody to raid out to. All right. Nope. Yep. Well, thank you, Penn Center. You too. Have a good one. Spent pretty good time at AMATYC, so I'll explain more about that next time if anybody's interested. Okay. Let's go make a new friend. Okay, okay. All right, let's go find this person. So, I'm gonna go select somebody named Ranigrad. Nope, Ranigad. And they are currently playing Outer Wilds. So, it's a favorite here. If you have not played Outer Wilds, I recommend it. It is on Game Pass, and it's also just worth paying for. Okay, so the volume is equal to pi times radius times twice the height. Oh no, raised to. So it's not twice, it's not times 2. Yep, so pi r squared times height. No. So, or at least not in a physical sense. There is no such thing as a centimeter to the 4th or 5th power. So there are some constants which have no real like physical meaning, um, whose units end up like just basically fixing the units that are all throughout the rest of everything. To make sure that, and this is important, right? Whenever you're doing volume, you're going to be looking for something cute, or liters, or an actual measurement of volume itself. Liters being the big one, gallons, that sort of thing. All right, let's start this raid. If anybody is interested, again, like I said, who's it's Outer Wilds is an adventure space game. So if you're interested in like weird mysteries that you don't know exactly what's going on, this is really the place to be. Um, I hope you all have a good couple of days. I'm probably going to be doing some fun random stuff during the week and maybe doing some more streams. We'll see how I feel. Because right now, I'm kind of tired. But that doesn't mean I'm going to go to bed. All right. Everybody have a good night. I'll see you at the very worst on Friday for more Astroneer. We're going to try and fix up the base and see what's new. So, have fun, everybody. See you later. This is Obi-Wan Pez for N Simplex Pachinko. Have a good night. Oh, I'm going to definitely feel better, too. Whoa.